before, and we skip all events for a certain period. Okay? So the muon Vito lowered the amount of muons by a factor of 4 order magnitude. So we start from 1, we put the detector underground, we gain 6 order of magnitude, but it's not enough. We have to realize this muon Vito and to gain other 4 order of magnitude. Okay. So this is just an exercise, just in order to look at how many neutrinos we expect. I said that the number of electron neutrino that reach the surface of this planet is in the order of 60 billion, 6, 10 to 10. 6, 10 to 10 neutrino per square centimeter per second. 10% of them is due to the Beryllium 7 line. As I said before, our main focus is to detect the monochromatic line of Beryllium 7. So we are looking for something on the order of 5 billion neutrino per square centimeter per second. The cross section of the elastic scattering is of this order of magnitude, the dependent energy, in the case of the order of 10 to minus 45 square centimeter. So if you made some calculation, you find out that in the energy between, for example, 250 and 100 keV, this is what we named the neutrino windows in order to see this line, you expect something on the order of 45 events per day in 100 ton of artificial volume. Okay? I want to come back in just a minute. Here, this part is composed by 300 tons of liquid scintillator. But we have radioactivity coming also from the nylon and the gammas from photomultiplier and from the sphere itself. Okay, so there is much more events here than in the very center. So if we can, when I say that for us it's important to reconstruct the position, it's because we can choose events that come here, then here, for example. So we can, thanks to the time of flight, reconstruct the position in order to make a fiducial volume that is no physical volume. It's by software that we can cut the radio in order to maximize the signal to noise ratio. Okay? Because if you have, for example, uranium and thorium everywhere, you have the same amount everywhere inside the balloon. But gammas from outside are more likely we will see some spectra later on. You have a lot of events here that for sure are background and not signal. Okay? So if we discriminate, we can take only the first 3 meters. This is, as I said, 8.5. This means that the radio is 425. I keep only the first 3 meters. Okay, so I eliminate this one, and I have, if you count, this 300 ton becomes 100 tons. This is why I am referring always to 100 tons. Every number I will give is referred to this volume. Okay? So, if we start with this flux, knowing this cross section, we expect about 45 events per day. Taking into account the fact that some of them oscillate with another kind, we expect roughly 30 events per day in 100 tons. This is a very huge number compared, if you remember, in the case of a mistake, as I said at the beginning, 1 atom every 6 days. 1 atom means 1 neutrino captured every 6 days. We have 30 events per day. this is quite rough. But I say that you have to fight against radioactivity, and radioactivity is everywhere, in particular uranium and thorium. So, how many events we have for a certain amount of thorium or uranium inside the scintillator? If I suppose, for example, to have a contamination in uranium and thorium at the level of 10 to minus 16 gram per gram, suppose that I am able to reach this contribution. You will see how difficult it is. You can put the number, for example, 1 gram of uranium 238 give about 12,000 becquerel, 12,000 decay per second. 1 gram of thorium give about 4,000 events per second. If we put this number and you look at 100 tons, you found that you have 20 events. So, even if you reach a level of radio purity on the order of 10 to minus 16 gram per gram, you have about 20 events per day, 100 tons of physical volume, compared to 30. So, this is the number you have to reach in order to have a signal to noise ratio on the order of 1. But, what does it mean, 10 to minus 16? If I get, for example, this center of rock, you discover that, okay, the uranium and thorium depend on the rock, depend on the position of the earth, so do you want. But, roughly is on the order of ppm, part per million. Part per million means 10 to minus 6 gram per gram. So, in order to reach such a level, I have to gain 10 orders of magnitude. Okay, I start with pseudocumene, that is our solvent, and I have to purify it in order to reach this amount. Okay? So, for this reason, in 1998 was constructed the counting test facility, the little detector I showed before, this one. You can see here, for example, this one. In order to prove the feasibility to reach such amount of radioactivity, and we are able to reach it because it's simply to reach 10 to minus 16, but in small cases. If you have some gram, maybe some liter of this, but you have to purify 100 tons of scintillator. So we proved that we were able to do that, and we made this by distillation, distilling the scintillator, water extraction. Don't know if I have time to speak about, maybe in the question if you want, maybe you can speak about tank with which procedure we are able to purify at this level. In any case, distillation, water extraction, natron stripping, and so on, different kind of techniques. So, radioactivity is not only uranium-238 and thorium-232, there are also uranium-235, but it's only 1/20th of this one. We have carbon-14. Carbon-14 is created by cosmic ray when interact with nitrogen in high atmosphere. So everybody of you know the carbon-14 techniques in order to find out how many time a body was dead and so on. Okay. We start from a scintillator, carbon-based, is an organic scintillator, and we have always carbon-14. This is why we have a threshold that is 200 kV, because carbon-14 undergo a beta decay, emitting an electron that has a endpoint of 156 kV. If you take into account the resolution that is not infinite, these 156 become 200 kV. So this is why we have a threshold that is 200 kV. If, for example, somebody found out a scintillator not carbon-based, we can lower the threshold